Good morning, everyone. It's 10:15. Welcome to our Saturday Physics for Everyone lecture. My name is Jan Shenla. I'm a professor here in physics and also the associate head for undergraduate programs. Before we start, a couple quick announcements. One is for any audience members, if you're interested in being on the email list to get notifications about these events, there's a sign-up sheet in the back on one of the desks that you can sign up. And related to that, I understand that there might be some high school students from St. Thomas More. Your teacher, Mr. Ray, has instructed us to let you know that you can sign on that same sheet so that your attendance here can be recorded. So please don't forget to do that before you leave for today. Okay, so let's get started. So it's my great pleasure to introduce today's speaker. It's Professor Kahn, who's a professor here in our physics department. Professor Kahn received his undergraduate education from Northwestern University, received his PhD in physics from MIT, and then was a postdoctoral fellow in the Kavli Institute of Cosmological Physics at the University of Chicago and Princeton University. He joined our department in 2019. His area of research, he's a theoretical physicist and focuses on searching for dark matter, one of the big unsolved problems in cosmology and all of physics. And today's lecture is going to be interesting. It's going to be at the intersection of the arts and sciences, and I think it reflects Yoni's personal trajectory. When he was an undergrad at Northwestern University, he received 4 degrees, one in physics and math, or that's 2, and then also in music composition and music performance. So he's been playing the horn for over 25 years and has performed professionally with ensembles in New York City, Philadelphia, and Boston. And so this is going to be, I think, a really lively and interesting talks with lots of demos. So I think we're going to get lots of audience participation. So let's welcome Yoni, and I'm looking forward for a great talk.
Thanks so much. It's a pleasure to be here. My name is Yonatan, and in addition to doing physics, I also play the horn, or horns, as you can see both on the screen and on this table. And so as you go through this talk, I hope to introduce you to some interesting instruments, help define what makes an instrument, how can physics help us think about music, and vice versa. So to start, I think it's just important to note that physics and music go way, way, way back. Like as far back as kind of recorded civilization. So Pythagoras, famous for such things as the Pythagorean theorem, which I hope many of you have encountered somewhere in your education. But also, he was the first person to really understand that when you pluck a string and you hold it tight at certain places, the length of the vibration determines whether or not we find the sound to be pleasing or displeasing. That is basically the basis for all of music theory, consonance and dissonance, that is still true today, even though the music that the ancient Greeks probably listened to and composed probably sounded nothing like what we are familiar with as classical music today. One of the unfortunate things about studying both physics and music is that in physics, we actually think that we knew what went on 13.8 billion years ago. But if you study music, you just have to imagine what sound sounded like, 2,500 years ago. There are records of both, but it's a little bit harder to parse through the things that are a little bit more ephemeral in the universe. Okay, but with that said, then if you go to the Middle Ages, there's this quadrivium, which was sort of the basis of what we call now the liberal arts. And so we think of the liberal arts as, well, at least here at Illinois, the College of Liberal Arts and Sciences has astronomy, but then physics is in the engineering college. A little bit of an unusual situation here compared to a lot of places. But some other places like Northwestern, the physics department is also in the College of Arts and Sciences. Arts and sciences, so for them in the Middle Ages, it was arithmetic, geometry, astronomy, and music. And today we might think, okay, one of those seems like the odd one out. But to people, going back thousands of years, the study of music was as fundamental to understanding the universe as the study of physics or astronomy. And then going forward more to the modern era, many of the famous names that you might encounter in studies of electricity and magnetism, like Hermann von Helmholtz, Ohm, whose name we attach to the resistance of a certain device that controls current through a circuit. Ørsted, who figured out how magnetism worked. All of these people studied acoustics. And so actually Helmholtz is known both for introducing conservation of energy, but also for publishing this book called Sensations of Tone that was really the book that launched the field of psychoacoustics, how studying how sound is produced influences how we perceive the sound. Okay, so let's define music. So this, I think, was the definition that I got in my first composition class in college. So music is organized sound. There's lots of sounds. That's a sound. I probably wouldn't call that music. If a lot of people are clapping together, I might call that music because the sound is organized in some way. It's organized in time. So there's two things that physics can help with. So how do we describe sound in physical terms? So what is it that's happening that's actually making the sound? And then how can physics help us understand the organization of sound that makes music? So why do certain notes sound good or bad together? And what makes different instruments sound different? Okay, so the basic concept is this. Sound is a wave. Who's heard that before? Cool. So what is a wave? So there's three pictures of waves here. So this is an ocean wave. This is ripples from a pond, but I think this one really gets at it the best. So let's see if this thing plays. So that's a crowd doing the wave. Right? So any disturbance that propagates is a wave. So something changes, and it could be height, or it could be pressure, or it could be voltage in an electrical circuit. Something changes, and it moves some distance in some amount of time. Okay, so I see my son is very excited to help me do the first demonstration here, so can I have him come down and help me out? All right. So this is Micah, a physicist in training. All right, can you please hold this end? And let's see, let's walk this way. Okay, so I'm going to make a wave that's going to start at my end, and it's going to end at his end. And if you watch very, very carefully and he holds it really tight, you might be able to see it bounce back. All right, ready? Let's try again. So you should have seen a pulse that kind of looked like this traveling down the wave. Micah, do you want to try to make one? Yep. And if you do it fast enough, and can you hold really, really, really tight? And let's pull the string really tight. It kind of bounces back a little bit. Thank you. All right, can you go back to Molly? So that was called a transverse wave because the displacement of that tube was perpendicular to the direction of motion. The wave moved that way, but the displacement was like this. There's another kind of wave that hopefully, if I put this at the right place on the table, should be easy to see. That's called a longitudinal wave. And this is a little bit harder to picture, but basically what's happening is, maybe, I think I can pin it down like this, yeah. So if you watch this slinky, I'm going to send a pulse, but I'm going to compress the springs of the slinky. And you can kind of see that pulse traveling down the slinky. So the direction of the thing that's changing, the compression of the slinky, is in the same direction of motion. That's what sound is. So sound is longitudinal waves. What is waving? It's the air pressure. Air is gradually compressing and expanding, compressing and expanding. So that's actually how we hear. Our ear perceives variations in air pressure. And that's how these microphones work. So microphones are just a way of converting a change in air pressure to a change in distance between two metal plates that changes the voltage in a circuit. And so we'll see a couple demos in a little bit where somebody, me or maybe one of the audience members, will make a sound, we'll record it through the microphones, and then we'll play it back through various devices just to show that indeed the thing that is being recorded we can then reperceive as sound. Okay. So there's a very important concept associated with waves that's called superposition and its cousin interference. And so to really understand this, it helps to use some math in order to make pretty pictures, which is really the best use for math. Okay, so this is a program called Mathematica that helps me make nice plots of things. So I'm going to plot a bump that's going to travel at some speed along one direction, okay? So there it is. Right? So that's like that pulse on the string that I made with Micah just a second ago. All right? Let's make one that moves in the opposite direction. Okay, that's not so hard to do. So now, before I show you the next thing, imagine what might happen if two of these things collided. Would they destroy each other? Would they be changed in some way? after they pass through one another, or they just pass through one another as if nothing happened. So just... So what's interesting, I think, is that the right answer is kind of a combination of all of the above. So let's watch. Okay, so something really interesting happens in the middle. Okay, so they combine to make one big bump, but then once they are past each other, now it's like they return to their original form and nothing has changed. Okay, so this is known as superposition or constructive interference. When these things are the same height, they add together and they make a bigger wave. Okay, what if I turn the second one upside down? Okay, so now let me pause this right in the middle. Okay, so if I rewind the tape just a little bit, right in the middle, there's nothing. They cancel each other out exactly. So because the thing that's varying can either vary in a positive direction, I can have more air pressure than average, or less air pressure than average, I can have either superposition, things adding together, or interference, or things are canceling out. The combination of those two things is extremely important for understanding how sound works. Okay, so we'll go back to the pretty pictures in a second. So how do we use waves to make music? Okay, so once again, that sound, that was a sharp pulse. So when I clap, I create some, there's some energy released in my clapping that goes into compression of air. That pulse then travels out to all of you, but then it stops and it doesn't continue. When you hear a sustained note, like if I played one on my horn, right, you're hearing that for a long time. So something must be going for a long time. So what is it that's going? So something is repeating over and over and over again. In physics, we call that a periodic function. Something is causing the air to be compressed and expanded in a periodic fashion. And the simplest functions that do that are trigonometric functions. And so this is something that hopefully most of you, if you're taking some kind of high school physics or pre-calculus, you've encountered these things before. But if you haven't seen this, it doesn't matter. A sine function is just a function that goes up and down a prescribed number of times per second, say. So if the x-axis of this plot was in seconds, this is a function whose frequency, f, is 5 humps per second. Okay, so it undergoes one full cycle every 0.2 seconds. So to prove to you that these things make music, let's plot one of these functions. So here I'm zooming in on a function whose frequency is 440 hertz. So if you heard A440, that's the sound that the oboe makes everybody tune to at the beginning of an orchestra concert. That's 440 oscillations a second. This doesn't look like any oscillations because I've zoomed way in. If I start zooming out, you can see that there's this repeating thing over and over and over and over again. And then if I really zoom out, it kind of all blurs together. And it's hard to see that, but it's very easy to hear it. So hopefully this should go through the room. Okay, so that's what a sine tone sounds like, right? That probably doesn't sound much like an oboe, but we'll see how to sort of build up more complicated instruments from simple sounds in just a little bit. Okay, what happens if we do that thing where we add two waves together? So let's play two notes simultaneously. Okay, so I'm going to play one note with a frequency of 550 hertz, and another note with a frequency of 440 hertz. So those of you that have taken music theory, maybe think to yourself what this might sound like before I play it. Okay, so if you know a little music theory, that's called a major third. So that's the notes A and C sharp. And you'll notice that these are nice round numbers, 5 and 4. So the ratio of the frequencies is 5 to 4. This is one of the things that Pythagoras figured out that makes consonant intervals things that sound nice. And if I wanted to plot it, so I'm going to plot it, but I'm going to slow it way down because human hearing likes to hear things that oscillate hundreds of times per second. But here, I'm just going to factor out this factor of 110. This is two waves with ratios of 5 to 4 plotted over a couple periods. That looks pretty complicated, right? It looks nothing like one simple oscillation, but yet our ear perceives it as something nice. So there's something kind of neat that happens when you play two notes that want to be exactly the same frequency, but they're a little bit off. So here I'm going to plot something with a frequency of 2 and something else with a frequency of 2 plus a little bit. Let's see what happens. So if the frequencies line up exactly, everything interferes constructively. But if they don't, so as I slide this knob, I'm going to make the thing go a little bit out of tune. And you can see that there's kind of this oscillating envelope, but there are these zeros where everything cancels out, so it interferes destructively. There's a term for that in acoustics. It's called beats. And I want to demonstrate to you that you can actually hear it. So let's see if this works. So I'm going to play an F, which is the note that the horn likes to play. And I'm going to try to go very slightly out of tune with it. And what you should listen for is kind of a wah, 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 wah sound that gets faster the more out of tune I am and slower the more in tune I am. So let's try this. Yeah, so it's a little bit hard on the version of the French horn that you see in the orchestra to deliberately play really out of tune. You'll see it's a little bit easier on this thing right here. But so who is able to hear that kind of wah, wah, wah? Yeah, so it's a thing where like your ear tells you exactly what's going on, but it really does literally correspond to these plots that we're making here. At those beat frequencies, it's the difference of the two frequencies of the notes that are a little bit out of tune, the pressure difference vanishes, and your ear perceives that there's no sound. So those beats are the absence of sound, and you hear a note, and then superimposed on it, you hear this oscillation. And actually, that's how piano tuners work. If you ever had your piano tuned and you hear a guy in your house like constantly making these wah, 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 wah things, it's because you can precisely tune the difference in frequencies between two notes by hitting a tuning fork and listening for the frequency of the beats.
So why did it feel uncomfortable?
Why did it feel uncomfortable? I think we'll get to that in just a little bit. So there are certain, so what is it makes the sound displeasing? We'll get to that hopefully in the next 15 minutes or so. Okay. How do you get an oscillating thing that just oscillates in time when I said that waves are things that travel? Well, it turns out that if you remember that demonstration here where I said that you can look at the wave pulse and see it reflected back to you, if you send a wave pulse down a string or a tube or something at exactly the right wavelength, so the distance between oscillations, it will bounce back and interfere with itself constructively and make a wave that looks like it's actually not moving. So to do that, I have to have a wave that moves to the left and to the right. And so here in this little demonstration, so the green wave is moving to the right, the blue wave is moving to the left, but their superposition looks like it just stays in place and oscillates up and down. And so to see this in real life, so this is a string. This is just a mechanical version of me waving the thing. And I have a knob that lets me tune the wavelength of oscillation. So if I do this just right, you should start to see an oscillation develop that, okay. So if you watch really closely as I turn the knob up, you'll start to see, you can see something kind of moving back and forth across the string. And then eventually, when I hit the right frequency, it's a little bit unstable. Let's see, maybe. There we go. Okay. So at this point and this point, nothing is really moving. In the middle, it's oscillating up and down, and you can count 1, 2, 3 oscillations over the whole length of the string. Those are those whole number ratios that will give us, actually, nice musical intervals. Okay. So you might well ask, do real instruments actually make sound anything like this? So in order to try this out, I want to try recording some sounds, and then we're going to look at their oscillations and see that inside them we can see these repeating patterns. So this is where I'd like some audience participation, but just because I don't want to make anybody do this first, I'm going to do this first. So let's see. Well, I've got a bunch of different things that I could play here, but this thing, if you want to make a horn at home, it turns out that all you need is a garden hose and a funnel. The horn mouthpiece helps a little bit, but if I stick a mouthpiece in this thing, let's see what this sounds like here. Kind of like a horn, right? Okay, so let me, hold your applause, there'll be a lot more of that. Okay, so I'm gonna record something, and then we're gonna look at it. So I can go over here. I want just a note that doesn't change in pitch, and it's a little bit hard on this kind of not really instrument. Let's try again. Okay, so there was a nice long note that was mostly at the same pitch, so your ear perceives it as kind of being the same note. So let's look at that thing. So what do I have here is I have a program that is taking in sound that's coming in from those microphones, and it's converting it to some digital format that I can later play back through other things if I wanted to. So let's see, if I play this note and make sure that it's playing through the room, right, that's kind of similar to the sound that you heard. Let's zoom in on that thing. So let's make this thing bigger so we can all see it, and let's zoom in time, right? This should remind you of that, right? That blob, there's a lot of oscillations there, but it's hard for you to see it, so we're gonna zoom in. Okay, so what we see is an oscillation that's repeating in time, right? It's something that has the same shape, and it's repeating over and over again, but it's more complicated than just one hump every some number of seconds. So I want to get a couple volunteers to try to make some different sounds. Okay, I see. All right, so the first person to raise your hand, feel free to come on down. Maybe in the front. Okay, and then I'll take you in the back a little bit. Kristen, I guess this means you're off the hook. Okay. It'd be great to either get a whistle, or do you want to sing a note? Okay, great. So can you go up to those microphones? It doesn't. You can sing any note you want. It just needs to be the same note. All right. Go ahead when you're ready. Fantastic. Okay. Thank you. All right. Let's zoom in on that. We need to make this thing a little bit bigger because that sound was a little bit softer, so the amplitude was smaller. There it is. Okay. So we see that, so over the course of that note, the character of the sound changed a little bit, and you can actually see that in the waveform, right? There's periods of time where the wave looks very similar, and then a little bit later, it kind of changes shape a little bit. So we're going to talk about how that actually affects our perception of the sound. Does somebody want to try whistling? Okay, I saw you first. I know whistling on demand can be very tricky, but thank you for your forbearance. Okay, go ahead whenever you're ready. Great, thank you. All right, so let's zoom in on that. You notice how this one looks a lot less complicated, right? It looks much more just like a couple oscillations over and over and over, and that's kind of it. That sounds more like those pure sine tones that I played earlier. And that kind of makes sense from the psychoacoustics perspective. Like, a whistle is a less complex sound than the human voice. So again, by the end of this lecture, you should hopefully be able to understand a little bit about how we can tell the difference between those two things. Okay, so just to show you that actually what's going on is sound is just oscillations, I'm going to try to play some of those sounds back through this thing right here, which in our electronics, or electricity and magnetism class, we use as a demonstration of the magnetic force, but here I'm going to use it as a not great amplifier. So let me just find one of the louder sounds first. All right, that was the voice. Let's see, where was the horn? That'll be a little bit easier to hear. Let's see. Let's see. Oh, that's my voice. Ah, there it is. Great. OK, so let's boost the sound on that a little bit so it's a little bit louder. And let's change these inputs to. OK, so what we have here is a piece of aluminum foil between the poles of a magnet. When I plug my computer into this thing, it sends a current through this wire that varies in time exactly according to this waveform up here. But the electrons that are flowing back and forth in this thing respond to the fact that they're in the poles of a magnet by moving a little bit. That causes this thing to vibrate, but the frequency at which it vibrates is exactly equal to the frequencies up here. So if everything goes right, you should hear the same sound out of this thing as we heard through the room. So let's see if this works. We tested this out earlier, but so I'm going to change now the input to, so my external headphones are going into this thing. So listen carefully. Can anybody hear that? So just to prove to you that it is actually coming out of here, I'm going to switch it back to the room so you can hear where it's coming from a different place spatially, right? So that's the room speakers. And then that's the same sound coming out from there. In a second, we'll see what happens when I try to put a really low frequency through this thing. Low frequency means the vibrations are very slow, and you can really see the thing just kind of flop back and forth. It's not very good at transmitting low frequencies. That's why the sound might sound a little bit tinny. So a tinny kind of sound means that the high frequencies are easier for your ear to hear. That's why you need big things like subwoofers to actually hear bass notes. So, OK. Let's see. Great. So we did some volunteers. Sorry, there's a question? Yeah. Almost certainly, and that'd be a great thing to try in just a little bit. Once we get to this thing called the Fourier transform. OK, so now we're getting into mathematics that might be a little bit more involved than maybe some of you have seen before. I just want to make sure that we're on the right part of the talk. OK, so we saw that we can add a bunch of different waves together to get more interesting looking waves. So it turns out that mathematics that was developed in the 19th century tells us that we can actually run that process in reverse. We can take any repeating function, any periodic function, and we can decompose it into a bunch of different simple waves, all with different frequencies. So there's a fancy name for this, and it's called the Fourier transform. But actually, this is what your ear does and your brain does without you even thinking about it. So in some sense, human audio processing is already performing this kind of trick. To show you how this works, I'm going to, again, record a note, and then we're going to look at it in a slightly different way. So let me go back to this program. Let's see. Playback device. Yep. OK. So let's record another note on the horn. OK, so instead of looking at the fairly complicated waveform, I'm going to use one of these fancy tools these audio programs now have, and I'm going to plot the spectrum. So what does that mean? So what this means is that hiding inside that much more complicated waveform is a bunch of different simple oscillations of different frequencies. And this program can pick them out. So the first one says that the peak frequency is this F. And so indeed, I was playing a note that was in tune, so that's good. But then there's another peak over here that's also an F, but twice the frequency, 1 octave higher. You probably didn't hear that. That's actually not an easy note to play on the horn, a note that's way up high. But that oscillation is inside that sound. And indeed, so is another one, and another one, and another one, and another one, and another one. And it kind of goes down this pretty nice and pleasing pattern. So if I didn't use the horn, this is an instrument called a shofar. So it's a ram's horn that it's used in the Jewish tradition, but it's much like a conch shell. So it's a very short tube that I can create an oscillation in. So if I try to play a note using that thing, you're going to see that it looks quite different. So. Okay, so that, you can play quite loud. The pitch is a little bit tricky. If I try to analyze this, things kind of look not as regular. Like there's a bunch of these very high peaks at very high frequencies. They're not necessarily in obvious relation to one another. And that kind of has to do with the transition from natural instruments that, this literally is an instrument found in nature. It's a ram's horn that's been hollowed out and filed down, versus the instruments that you would see in the orchestra 150 years ago versus the instruments that you would see in the orchestra today. So let's start talking about that. So in that horn sound, so what did we see? Okay, so this is me playing another note the other day, and so the frequencies are a little bit different. But if you actually go and look at the numbers that were there in that plot, I have the frequency of the note that I hear, twice that, 3 times that, 4 times that. Each one of those peaks is very, very, very close to one of these integer multiples of the frequencies that I started with. This is not an accident. So musical instruments are designed so that the instrument wants to vibrate at those special frequencies. Those integer patterns of frequencies are called the harmonic series. Okay, so this is a plot of the first 8 multiples of some low bass frequency. So again, the visual example here is, so the lowest frequency would be the one where there's sort of a standing wave that oscillates the entire string, and then one where there's kind of a gap in the middle. Can I find it? There. So there's kind of 2 waves here. Then if I turn it up more, there's, where was it? Somewhere in there is 3 waves. I think you saw it before. Okay, kind of getting it there. And so on. So these integer multiples, again, are the ways that you get this standing wave that gets reflected back at exactly the right speed. Let's play this. Shift it up a little bit so that it sounds like the frequencies that I would play on the horn. So take a listen. Okay, anybody here play a brass instrument? Does that sound familiar to you? Yeah, so those are the notes that you would get from an open tube. So this is called a natural horn. So back in the day, horns were used for signaling on horseback, and they were just tubes. If I stick in a tube with the right length, those are exactly the notes. So the horn likes to resonate at multiples of a certain lowest frequency determined by the length of the tube that I stick in. There's a cool other example I could do with this garden hose. Maybe if people want to come down and ask me about it after, if I attach 2 of these garden hoses together, I can change the length of the tube, therefore changing the frequency of the lowest oscillation. But you might notice that if you keep going, things start to sound a little bit out of tune. Right, so there's some there that probably bothered you. I'll play them. It sounds a little bit less bad when I play it on the horn, but that strikes your ears as a bit weird. But that is what nature gives us, in fact. So there are just some notes that are integer multiples of a fundamental that our ear somehow feels is a little bit displeasing. And again, I'm going to turn the volume down because I don't want to cause you pain. But if I tried playing 2 of those bad notes together, you're not going to like it. Right? That's like the sound that goes on your radio when there's an emergency, right? It gets your attention and then says, okay. Right. So the history of brass instruments is basically about how do we fix those bad notes to make a sound that as humans we like better. So what's really going on is that we like integer multiples, but not integers that are too large. Like here, that was 12 and 13. So the greatest common denominator, or greatest common factor of 12 and 13 is some enormous number of oscillations, whereas the greatest common factor, the least common multiple of like 4 and 5 is 20. I only need 5 oscillations of frequency 4 or 4 oscillations of frequency 5 before I get back to the beginning. Your ear doesn't like things that take too long to repeat. That's basically the one kind of sentence lesson of psychoacoustics. And so people came up with these brilliant ways of fixing the notes on the horn. So watch this. I can make that note sound in tune because as I put my hand in the bell, so I'll kind of swing this around so you can all see it. By covering the bell with your hand, you can change the pitch. The character of the sound changes a little bit, and we'll come back to that. But at the very least, you now have an instrument that can actually play scales. Right? How did I do that? I move my hand around in the bell fast enough, and what's amazing is that like the theory of acoustics took 100 years to catch up with what people just figured out just by messing around. Like back in the late 1700s, there were people who literally their entire job was to just play music that people wrote for them. They were probably a little bit bored, and they were probably just messing around one day and realized, oh my God, I can just get all these different sounds. And so I actually really enjoy playing this instrument because it gets me more in touch with the way that composers would have written for the instrument when that's all they had. So the first thing is that the sound is loudest when you use the notes the instrument wants to play. So I'm going to play something. Hopefully you'll find it familiar. Whoops. What? Anybody? Yeah? So it turns out that, okay, that was a little bit of a lie. The horns don't actually play there. They play this thing. Right? But like, when you really want a loud horn sound, you play all of the open notes. Because if you wanted to finish the opening of that, you can play that note, but it changes the sound in a little bit. And so early on in the development of this technique, composers kind of avoided it unless they had to. Then they realized that, oh, actually, like, that different sound is quite beautiful. And you can do all kinds of things, like you can play in keys the instrument doesn't really want to play in. So here's a scale. Here's another one. So I can play an A-flat major scale on a horn that wants to play in C by putting my hand in the right positions all the time. And actually, it kind of gives the horn some of its character of kind of this kind of far-off nostalgic instrument. As you kind of cover, you kind of get this like far-off distant sound that I think is actually quite beautiful. And understanding what makes it work is kind of where I think that the intersection of physics and music, really helps me actually as a musician. Okay, so let's see, where were we? Let's do a couple different examples of notes on the horn but played in slightly different ways. So here I'm going to stick with this, this natural instrument. So one thing that I can do is put in the shortest possible tube. And let me record this sound. Oops. Sounds almost like a trumpet, right? So if I take that last note and I expand its spectrum, which are basically counting up all those different peaks, I get something that looks like this. Okay? I'm now going to stick in a tube that is twice as long as that one, or rather, I'm going to make the whole horn twice as long, and we're going to compare these things. So actually, let me just take a screenshot of this so we remember what that was. And okay, let's put this down here. Oops, uh-oh. Why did that not work? Let's try this again. There it is. Okay. Now let's do that again with this longer tube. You can tell that I'm working a little bit harder to get that note, because actually, the notes that this horn wants to play are all of those notes. By making it twice as long, our ear perceives the notes as being closer together. And let's see, is that the note? Yep, that's it. So let's look at its spectrum. And let's compare this. Right, so your ear perceives these two things as the same pitch, but there's an obvious difference, which is that the higher harmonics are more prevalent when the tube is longer. That's why the sound feels a little bit more strained, maybe, or maybe that's a good thing if you're a composer. You want to feel like you're a little bit on the edge of something, whereas the kind of music that you would play with a tube this short would probably be things like, right? That's what this is good for. Or that's more of a trumpet thing, so you can see it's not really meant to play notes quite that high. But you wouldn't want to try doing that on this horn. It would sound a little bit like trying to drive an 18-wheeler truck as a race car. You have to figure out what thing is going to work best on the horn that you want. Though this is very good for kind of these slow, beautiful kind of passages. Okay, so there's one more thing that I want to show you, which is the difference between those open and closed notes, that you can really see it again on these spectra. So let me do one more. So let's try recording this note. And then which again on the natural horn is the only way to play that other note. The horn wants to go, but I'm making it go. And the price I pay is that it sounds a little bit different. But again, maybe that's a price that I want to pay because it does something in the music that I want it to do. So let's see. My voice is hard to distinguish from the horn sounds here. Right. So that was the closed note. And then the open note was, nope. Where was it? There it is. Okay. So that's the open note. Oops. And then if I do the same thing with the other one, okay, so what you notice here is that actually, in that first case, the second harmonic is very, very strong. So there's actually a lot of, there's actually a lot of that note in the lower note. Whereas in this other one over here, there aren't a lot of those other harmonics. It drops out very, very fast. The reason it sounds a little bit muffled is, again, that the horn doesn't want to resonate at those frequencies. You're kind of forcing it to. That forcing of the sound means that also the proportion of the higher harmonics that are there don't fall off as fast. So the perception of a sound that's a little bit brighter or brassier, if I try really hard, I can get this thing to buzz. And actually, that technique is used on the modern orchestral horn all the time. Anybody's ever played music by the composer Gustav Mahler and you're a horn player, you hear that sound all over the place. It's deliberately trying to make it buzzy, whereas back in the day, that's kind of the only option they had. Okay, so having done all these demonstrations, this is kind of the summary, is that timbre, which is a musical term, the way that we perceive the quality of the sound, can be translated to the spectrum. In other words, the proportion of the higher frequencies that are present in that sound. And the way that you describe a sound in words, is it brassy or is it reedy? Is it clear or is it muddy? Is it resonant or is it dull? We've seen several examples of all this here. You can perceive the same note, but the quality of the sound is different depending on the spectrum. So this is trying to show those two at once. So the open note was the red, and the closed note, which again is higher in frequency, so all these peaks are a little bit displaced, is the blue. And you can see that in the red, it falls off much faster, but in the blue, it stays for a longer time. And so a game that one can imagine playing is, if somebody gives you a spectrum, can you guess what the quality of the sound is going to be? Actually, there were early ideas in the early history of recorded sound of this being a way that deaf people could hear music. If you printed out the trace of the sound, somehow you'd be able to interpret what was actually going on. It's hard because the psychoacoustics is more complicated than that, but it was definitely the right idea. Okay, let's see, so I have until 11:15, right? So there's one last thing that I want to try doing, which is inverting this process. Let's build up an instrument from waves. And so here, Kristen, I think this is actually where I think it'd be really neat to try what you suggested. So we're going to record a sound, we're going to look at the spectrum, and then we're going to try to add up the waves one by one to make a sound that is as close as possible to the one that we recorded. It's not going to work exactly because you need a lot of waves to make this work, but hopefully this demonstration will show this is the right idea. You want to come down and help out? So let's, so the thing that Kristen was referring to, so head voice or chest voice, you might know them better as like falsetto. If you hear somebody yodeling, that difference in sound is changing the part of your body that's vibrating. I'm not a singer, so I'm not going to attempt to explain it beyond that. But why don't you pick some technique and some note, and let's record it. Go ahead.
Actually, I could demo that with a little.
Sure. Do you want to try? Yeah.
So that's like the difference between that's head voice versus like oh Fortuna. It's very chesty.
Right. So the timbre is different, and so hopefully we should see it. All right. So pick whichever one is your favorite, and go ahead. Awesome, thank you. Okay, so here's what we're gonna do. So we're going to export this thing, and we're gonna import it into this other document. So let's see. So what is this thing called? Teaching Saturday Physics for Everyone. Voice. Okay. Let's do that. Now, oops, if all works well, I should be able to import that thing and play it back. Uh-oh, oops, I know what's going on. Come on. There it is. Okay, so there's Kristen. And then what this program can do is, so making the plot of the spectrum is called making the periodogram. So there it is. When you look at it on a linear scale, Like, this is absolute air pressure difference. You really only see 2 peaks, and you can see they're pretty clearly separated by a factor of 2. So you see the note that you heard, and then kind of the fundamental 1 octave above it. But if you plot it on a logarithmic scale, so logarithms are inverses of exponentials, so that's another function you might encounter in a pre-calculus class, we actually perceive sound logarithmically, meaning that something that is, let's see, which way did this go? So something that is 4 times as loud, or 8 times as loud, or 16 times as loud, we kind of perceive sound in intervals like that. And so if you do that and you kind of zoom in, now you see a lot more stuff going on, okay? And I can actually extend the range because that was a fairly high note, so maybe there's even more things. So let me kind of see. There's a peak there, there's a peak there, there's a peak there, there's a peak there, there's a peak there. Let me see what happens if I add up these peaks with the right amplitudes, and we'll see if we get a sound that sounds anything like what Kristen just sang. So if I look at the numbers on the y-axis, so this is like 10. So what frequency are we at? Let's see, 200, 400, 600, I don't know, let's say 610 seemed like a good guess. And then I'm going to guess that all these are integer multiples of the same thing. So, so the amplitude of the first one here, this is like, I don't know, maybe 10.5. And then the other amplitude is like, I don't know, 15. I just look at the numbers on the y-axis. This is like minus 15. Let's say this is minus 20. Let's add these things up. Let's see if we get anything that looks roughly like the waveform. So, okay. So this is.
You don't have 15.5.
Oh, whoops. Which one was 15? Oh, 15.
You had 15 dot.
Oh, good. So that should be, yeah, okay, sure. I'm kind of eyeballing things. I'm probably wrong by a little bit, but we'll see that it does make a difference. Okay. So that's just 1 wave. That's 2 waves. That's 3 waves. That's 4 waves. Let's see, if I did this right, this should look a little bit like what happens if I go back here and zoom in on the waveform. So, and again, I was kind of averaging over, so as she sang, the timbre changed a little bit, the harmonic content changed a little bit, so I'm not going to get it exactly right. But let's see what this sounds like when I add up these waves one at a time. So the first one is a pure sine tone. Then one more. Okay, so no one would ever confuse that with a voice. However, so that was head voice, right? Okay, so head voice has more of the higher harmonics, and so we kind of see that the result of doing this is a sound that sounds a little bit brighter, maybe it projects more. If we did this experiment again with the chest voice, we would probably see that we needed to add up more of the lower harmonics in order to get a sound that replicates what we see here. But this kind of thing is, again, what your ear and your brain just do automatically. So how you perceive 2 notes as sounding like a chord or just sounding like 1 note with a very complex sound, that's a whole separate can of worms that I'm not an expert in. That's the whole field of psychoacoustics. You can trick your brain into doing all kinds of crazy things. You can play sounds through 2 different ears at different rates, and you'll hear just the tone together. You can make your brain hear like a sound is going around in circles. There's a thing that's like an infinite staircase where you can hear a siren that appears to just rise in pitch forever, even though all it's doing is going back to where it started. It's like an audio version of the MC Escher staircase. The human brain is amazing. I have no idea why we evolved to be able to do these things. Yeah, there's just really, really cool stuff. So I just want to point out this kind of crazy fact about human hearing, which is that, okay, so the units of amplitude are decibels. So 10 decibels means stronger by a factor of 10, but confusingly 20 means stronger by a factor of 100, right? That's a logarithmic scale. So humans can detect sound over a range of 0 to 120 decibels. That doesn't sound that impressive until you convert from this logarithmic scale back to the actual scale. We can hear pressure variations over a range of 1 trillion. So at the very, very softest sounds that humans can hear, it's really like single kind of molecules that are vibrating. If you go up to 120 decibels, you lose your hearing forever because like once you basically blow out the amplifier that's your ear, you never get it back. So life lesson, if you hear loud sounds, always cover your ears or wear headphones. Really just doing this when the subway comes by, if you're in a big city, will preserve your hearing for a long time. But I mean, this is the point. So, this is why we couldn't get to a human voice by adding up 4 waves, because we can perceive even those very, very, very faint things that are way at the higher harmonic range of things. And this is why music is beautiful. So just to close, I've been playing the horn for a long time, so some of you that were here a couple years ago, you might have seen during the COVID lockdown, we did this art science festival. I kind of demonstrated some horn playing and some compositions from my living room. But what I've hoped to convince you is that knowing what physics goes into making a good sound actually helps. No matter what instrument you play, whether it's a string instrument or a wind instrument or a brass instrument, because then you can think about the thing you're trying to do, and then eventually when you practice enough, your body kind of takes over and does it automatically. But it's good to know actually what's going on underneath the hood. Also, I've just always found throughout my career that music is just a very nice mental break from physics, and so just separate entirely from the physics of sound, it's nice to be able to do something that doesn't resemble at all what I do for my day-to-day life. So with that, thanks so much for your attention. I'm happy to take questions.
Wonderful. So we have time for a few questions from the audience. Oh, there's one there. Yeah.
I'm a trumpet player, and I'm part of the marching Illini, and we get like really, really good trumpets. And I found that the really, really good one is much easier to play on some notes
Yep.
than the one I got from my cousin.
Yep. Yep. Yep.
But do you have any intuition why is that, or is it just that you're forcing the instrument?
No. You're exactly right. So this idea of the harmonic series, right, is actually, it's not what the instrument wants to do naturally. So this is actually more like a trumpet than a horn because it's a cylindrical tube. It doesn't change length, right? If I blow into this thing, well, first of all, without a mouthpiece, it doesn't lock in at all, right? What that means is that, so in order for it to lock in, the instrument needs to reflect the wave back to my lips, and then the higher pressure forces my lips to open at the right frequency that I'm trying to drive it at. There needs to be this like nonlinear resonance between the instrument and the thing making the vibrations. Putting a mouthpiece in helps a little bit. You can hear that it locks in. The bell helps even more. So. Right? You can hear the harmonics there. So really what's going on with the trumpet is that you are kind of jerry-rigging the instrument in order to make the resonances of the tube match the theoretical resonances of the harmonic series. And you can do a better or worse job at that. And not playing easily is that feeling of the note doesn't want to lock in. Right? And so those slots are basically a function of figuring out how to tweak the instrument to make those natural resonances the equally spaced harmonics.
Can you talk to the audience about what you're doing with your lips when because you're playing the different pitches on your lips,
Yeah,
right?
very good.
Yeah.
So all I do to make a sound on the horn is go, right? So my lips are bouncing off one another at a certain frequency. If I play into this mouthpiece, I can play any note I want on this thing. It's like a trombone with a slide. Nothing locks in. But if I try to drive it at a frequency that's not one of the ones that the horn wants to play, you hear that oscillation? That says that like the feedback between my lips and the horn doesn't work there, and I have to work really hard to try to play a note in the middle. It's easier on lower notes. Again, trumpet players know about these pedal tone warm-ups. Yeah. So question back there.
So I play horn, and I know that it's really easy, or it's like possible to hit like every partial with every finger.
Yeah. Yeah.
Can you repeat the question?
Yeah,
for the
so
audience?
using a little bit of horn player lingo, so it's possible to kind of almost play every note using whatever fingering you want. That's not exactly true, but it's true the higher up you play because they get so close together. So the notes the horn wants to play if I don't put any fingers down are. And so if I play high enough, I mean, there's something there. It's not exactly the right note. If you put your hand in the bell, you can bend it enough to get the same note. So but that's basically doing this thing if you're changing what the national resonances are. But the horn is so long that you're mostly playing in the part of the harmonic series where the notes are very close together. And having a bunch of like series that are very close together means you can kind of pick and choose which one you want. Yeah.
Okay, maybe one last question in the back over there.
So obviously you can have sound in the shape of like a curvy wave, but can you have it in the shape of a zigzag or even a line?
You absolutely can. That's an excellent question, and let's hear that. Okay? So what that's called is like a triangle wave. And so let's see if I can make this thing. So I just need to figure out what the right command is. Great. Let's plot triangle wave. Let's see, at A440. Oops. Shoot, why is this not working? This is the problem with trying to do this thing live. Ah, there we go. Okay, so let's do that. So if we play this thing, right? Not very pleasant because it looks so spiky, right? Let's zoom in on that thing. So, right, those sharp edges your ear does not like. What that means is there's a lot, if I decompose that into waves, it means the higher harmonics are kind of always there and they never go away. And that we perceive as being unpleasant. But yeah, you can make, this Fourier transform thing is you can always make a spiky shape. You just have to add up a lot of really smooth waves to do it.
All right. Let's thank Professor Kahn again for a wonderful presentation.